Thank you very much. I'd like to thank the organizers for allowing me to be here at this special place, and even more the seminar organizers here to allow me to speak. Choosing the topic, I thought I should try to, I can only give sort of motivic talks, and then I tried to give a talk which is somewhat closer to the equivariant situation. So I will talk about a very special group, the special linear group. So yeah, just so this will be over a field F. But yeah, if you like, and maybe that's easier for me, we can assume that the characteristic of the field is 0. If you're interested in the positive characteristic case, we can maybe talk after. And yeah, just to connect it with sort of more topology and also the previous talk, if we look at the special linear group over C, this contains SUN as a deformation retract, and the real points, this contains SON as a deformation retract if you equip these with the analytic topology. But sort of the idea is now, so due to Morel and Wygotsky, to get an A1 homotopy type out of every variety. And I don't want to get into the details of the A1 homotopy category. Let me just sort of remind you that the affine line is then the object that parameterizes homotopies. This is how it looks like. And if you have a variety over F, maybe I should like this, then there's a naive version to get an A1 homotopy type out of it. And for this, let me define the affine standard n simplex over F. So this would be corresponding to a polynomial ring in n+1 variables modulo the sum of these variables being 1. And so this, there's supposed to be some topology, so there should better be a picture in the talk. And here's the picture. If you want to draw delta 2, this should be in 3 space, and the boundary of delta 2 then looks like this here. Well, if you draw it better than me, right? So this here should be 1 point. Yeah, these are then sort of the standard unit vectors. Okay, and if we have, yeah, we have this variety, and then we get a Suslin construction in this context, get a simplicial set, and the n simplices, these are the varieties, variety morphisms from the affine n simplex to X. So since these give a co-simplicial object, we get here a simplicial set. And then this has homotopy groups, and let me sort of wrongly define ik A1 of X as the case homotopy group of this simplicial set. Let's assume that X is a pointed F variety. So this works only under special, sort of for special varieties, but for the varieties that I will give you in this talk, this is sort of the correct homotopy type, and the varieties I will show you, they have a, yeah, I should watch out now, they have a canonical base point. Of course, the canonical is up to debate, but for example, if we start with the group, I think it has a canonical base point. Okay. Yeah, let's start with the group. So let me give many names. GL1 or the affine line minus 0, or the multiplicative group. So this is this affine variety. And now if you want to look at this A1 homotopy type, you're looking at morphisms. This affine n simplex to X. I haven't said so, but sort of this delta n is really isomorphic to the spectrum of the polynomial ring in n variables. And if you look at what the morphisms to GL1 are, they correspond to the units in the global sections of the variety. And then there's this known fact that if you're over a field and you look at units in a polynomial ring over this field or units in the field, it's the same. Yes, so this thing of GL1, this is discrete. Because, yeah, what do we have here on GL1? So this corresponds to the units in this ring. Which is just the units in the field. And so this is not very interesting. But we can write down all the homotopy groups since it's discrete. Now let's make it more interesting. So in general, if you have a variety which may not be sort of connected, whose A1 homotopy type is not connected, in general there's no guarantee that you can sort of take the path component, take a path component and again get a variety. But here's a very special case. So we have the determinant homomorphism, where the special linear group is the kernel. So we have this short exact sequence. And when we look at this here, this actually is connected in this sense. So SLN is A1 connected. And one way to see this is to quote a theorem saying that, in particular over a field, these special linear matrices are generated by elementary matrices. So if you have an elementary matrix, it looks like this. You have some, I don't know, some A here somewhere, and there are units on the diagonal. And you can multiply this A with the parameter T coming from the homotopy there. And then everything is connected to the identity matrix. Okay, and here's another thing. This here is actually a nice fiber sequence. So on Sing, it induces a fiber sequence. So maybe the short term will be A1 fiber sequence. And this means that the higher homotopy groups of GLN and SLN, they do not differ. And then the idea is to find out something about these groups. So this here holds for all positive K N. And in order to sort of see what happens here, let's enlarge the N. So if you have a matrix A, you can enlarge it by placing single 1 here. That's n plus 1. Okay, and so there's another interesting map which takes the last column. Now, if you take the last column of an n plus 1 by n plus 1 matrix, it lands in a n plus 1. But you won't hit 0 if you start with a matrix which is invertible. So there is this inclusion here and this map. And now if you, say, take here the base point having 1 here and then zeros everywhere else, then the fiber here would not be SLN, but you would be allowed to write any stuff here. Well, but if you are allowed to write any stuff here, you can then shrink it to 0 by multiplying with t. So this is maybe enough justification to say that this here is also an A1 fiber sequence. Okay, there's actually a theorem behind that, but it's not so difficult. A more difficult theorem is the following, which is due to Morel. So he computed the first non-trivial homotopy group here. So the kth A1 homotopy group, yeah, and of this here is actually 0 if k is less than n, and then this is the Milnor-Witt k-theory in degree n plus 1 of the field if k is equal to n. And I can say, or maybe I should say what this here really is a little bit later. Let me just give you one hint for this 0 here, which is, yeah, I mean, if you've seen it before, it's maybe not so interesting. So here we have A2 minus 0, but think of it as an plus 1 minus 0. And we can cover this using these two guys. So they are glued along the product of A1 minus 0 with itself. And now what you can do is you can take sort of 1 as the base point. And then you get a wedge of 2 copies of the affine line in here, which you can shrink. And if you shrink, you pass here to the smash product. And what you then see is that A2 minus 0 is a union of 2 contractible things. A1, parametrizing all homotopies, is contractible over this here. So this means A2 minus 0 is equivalent to a simplicial suspension of the multiplicative group smashed with it once with itself. And here you see this is a simplicial suspension of something, so maybe it's not so surprising that this is then actually connected. And of course you can iterate this argument, and maybe I should introduce some confusing notation. Any questions so far? Enough groups for the Equivariant people? All the finite groups are there. Subgroups, if you like. Okay, so here's the confusing notation. So S1 will be the usual circle. And then there's also S1, S brackets 1, which will be this other circle, this Tate circle. And then if we have natural numbers S and W, there's an S plus brackets W sphere obtained by smashing all of these together. And then the sort of more general form of this equivalence is that an plus 1 minus 0, this is then equivalent to Sn plus brackets n plus 1. Okay. Okay, so yeah, with this, maybe the sort of first statement is quite plausible. And yeah, I'll get to the Milnor bit case theory a bit later. As a consequence, we get that pi k a1 of SLN, we write SLN plus 1. It does not depend on n if n is bigger than k. And the question is then, what is it? And there's another theorem. Let's see, now this is the shaded region. Maybe I can. So this appears in the Morel-Wołodzki publication. And here the positive natural number, and then pi k a1. Yeah, since we can enlarge n, let me just go to SL infinity. So the union of all the SLNs for n finite. And this is isomorphic to algebraic K-theory of the base field. And here's a bad choice of notation, of course. And just because there is at least one other flavor of K-theory, let me emphasize by Q that this is Quillen's higher algebraic K-theory. Okay. Maybe just as a sort of to quickly convince you that this is true, pi k a1 SL infinity, well, this must be the same as pi k plus 1 of BSL infinity. And we're here in the situation where k is positive, so this must be the same as pi k plus 1 of PTL infinity. And now there's one thing one has to check, and it's not so easy. If you take the Singh construction on BGL infinity, well, I only defined this for a variety, but this is a union of suitable varieties like Grassmannians. Okay, and this here actually gives you Quillen's class construction of on BGL infinity, and then you sort of get the statement. Okay, so this means that there are some answers to what the homotopy groups of the special linear groups are in terms of algebraic K groups. And now this is sort of this thing. There are only very few fields where all of these groups are sort of explicitly known, and all of these fields are finite. Okay. And yeah, I think I said characteristic 0. So this is now turns out to be a bad move. But anyhow, let's just take this as something which is sort of known. I mean, this is sort of something describable, something that we can work with. Yeah? Because yeah, the ones that come up besides this stable range here, they are then going to be slightly more complicated. Yeah, probably. So let's think of this here as not complicated. I should not really say this, and this is even sort of on screen now. Okay, from this A1 fiber sequence here, we get a long exact sequence of these homotopy groups, and this terminates somewhere. So here we have pi n A1, SLn plus 1, mapping to pi n A1. So this is the last column map to the n plus brackets n plus 1 sphere. Ah, right, I forgot to, yeah, no one complained. Okay, so I ignored the base field in the notation for the group. It should really be there, otherwise this here comes up sort of by surprise. But no one complained here, so no one was surprised. Good. So maybe no one is paying attention. Okay. So here we're at pi n minus 1 of this as n plus brackets n plus 1 sphere. So this here is going to be 0. So we have something surjective here. And what we have here is Quillen's K-theory of the field F in degree n due to this shift here. And what we have here is also sort of described in Morel's theorem. This is the Milnor-Witt K-theory of F in degree n plus 1. So we should be able to describe this here as an extension of this algebraic K group by a quotient of this here. And this would then be sort of the first non-stable case. So would anyone like to see a definition of the Milnor-Witt K-theory? Does anyone insist on not seeing the definition? Okay, this is almost in my calculus lecture, analysis lecture. This was a no? I didn't want to do it. Let's see. I would like to introduce some notation, and for this it would be convenient if I just quickly describe what this thing is. Well, let me not be too precise. So this is Z-graded algebra. And the generators have this form. These are in degree 1. And this walks through the units of the base field. And there's a single generator eta in degree -1, which is not the same eta as in Stefan's talk, but, well, it's not quite the same eta as from topology, but in fact it is. Yeah. So let's see. And then there are some relations. There's a Steinberg relation. These guys, yeah, so the unit and this here, these commute with each other. Let me write down what prevents this Milnor-Witt K-theory from being Milnor K-theory it's precisely eta. And then there's a Steinberg relation. Oh no, as I already said that, then there's a hyperbolic plane relation. So 2 plus minus 1 times eta times eta. This is 0. And this here is usually abbreviated as H, standing for the hyperbolic plane. And here's some more notation. Maybe let me put it here. So take a natural number n, and n epsilon, this is defined to be n half times h if n is even, and it's n minus 1 half times h plus 1 if n is odd. And so these are then elements in degree 0, and it turns out the degree 0, this is the Grothendieck-Witt group of symmetric bilinear forms over the field F. Any characteristic, but characteristic 0 here anyhow. So for negative degree, this turns out to be just the Wittering in every negative degree, Wittering of symmetric bilinear forms. And so for just the third flavor of K-theory, if you factor out the ideal generated by eta, you get what Milnor introduced in, was it the 70s or the late 60s, as a first approximation to higher algebraic K-theory. This is a non-negatively graded ring, Milnor K-theory. Okay, so we have this Milnor-Witt K-theory, Milnor K-theory, Quillen K-theory. That's all the flavors of K-theory, I think. So what? Right. Let's look at this here in a special simple case, namely for n being 2. Okay, how does this look like? We have pi 3, no, pi 2, SL3, mapping pi 2, that's 2 plus 3, and then we have pi 1, SL2, pi 1, SL3, and then there's a 0 here. Now, here we have the second algebraic K group of F, but by Matsumoto, this is the same as the second Milnor K group of F. Maybe I should write isomorphic here. SL2 is in fact also just a sphere, as one can see by projecting to sort of one row or one column. Okay, and what? Right, so this means that this here is by Morel's theorem, the Milnor-Witt K-theory, and this here is also Milnor-Witt K-theory, here in degree 3, here in degree 2. Now we have maps here in between, and then of course it depends on really what the isomorphisms are, if you want to say what the maps here are, but if they are chosen appropriately, then this here is the canonical map, which means it's this sort of projection to the quotient, which means that this here is then multiplication by eta, and this then tells us that sort of the image of this map here corresponds to the kernel of this map. Okay, and the kernel, yeah, it's sort of, it's the eta torsion in this group, and in general there's sort of this problem. If you if you are in such a Milnor-Witt K-theory group and you want to look at sort of something annihilating a single element, there's no guarantee that this is then generated by finitely many elements or a single element, or yeah, it's really it's a bit unfortunate with these groups. But in this special situation, this is a theorem of Gille, Scully, Chong. This is actually generated by the hyperbolic plane. So maybe let me write it here. So the kernel of multiplication by eta, here this is the same as the image when you multiply with the hyperbolic plane. Yeah, so Gille, Scully, Chong. Okay. So now it's about half time. So maybe it's actually time for a newer theorem. Newer than these already had on the board. This is just sort of preparation. And this is the next case then, n equals 3. So the image of pi3 SL4 in pi3 S3 plus brackets 4. This here is eta times k Milnor-Witt 5 f and a sum with 3 epsilon factorial times k Milnor-Witt 4. Yeah, I defined this n epsilon, and when you multiply these, you get the corresponding factorial. You multiply in the Grothendieck-Witt ring. Okay. Yeah.
3 plus 4 is 8, 4 minus 0, or?
Yes, it's A4 minus 0. It's the last column, this map here. Okay, and in particular, there exists an extension which describes now pi2 of SL3 you have the fourth Milnor K theory of F, mod 6, and you have the third algebraic K group of F. Yeah, and this in general is bigger than the Milnor K theory. Okay, and now there should be complaints that computation of a single homotopy group is called a theorem. Yeah. Yes. Yes. So this means 3 epsilon times 3 epsilon plus 1 epsilon. And this is the reason why I wanted to sort of introduce this here, so to have the hyperbolic plane, and then, yeah, this is the reason why I withstood your request. Yeah. Okay. And in fact, when you quotient out eta, you're just in the Milnor K theory, and there the epsilon goes away. So the 3 epsilon factorial is just 3 factorial, which is 6, which is the number. Okay. So no one complained that the computation of a single homotopy group should not be called a theorem. Okay, thank you for this argument. And there's another argument which connects maybe with the C2 equivariant situation if you're over the field of real numbers and you look at the Galois action. So we can look at more homotopy groups of some point at x by setting these to be morphisms in the A1 homotopy category from the S plus brackets W sphere to X. And there's a funny thing happening when you take a natural number W, sort of the weight, the amount of Tate twists. We get then an exact sequence from this exact sequence, which looks like 4 minus W. And here we have pi 2 plus brackets W. And here we have K3 minus W. Again, a theorem that sort of exactness is preserved. And let me just single out a special case. So the negative K groups of fields are all trivial. This is true for any regular thing. So we should look at the case W being 4. And there we have K Milnor 0. So this is just the integers mod 6. And this is pi 2 plus 4 A1 SL3. And now topologists should remember that pi 6 of SU3 is also Z mod 6. And this is the same 6.
Jim Davis said this wrong yesterday.
Pardon?
The algebraic topology mailing list, Jim Davis.
Yes, yes, yes.
Yeah.
Yeah, right. Thank you for reminding me. I read this just before lunch and was very happy to see this, because this is actually, I mean, there's a theorem which is due to Borel-Hirzebruch, and which is 2n, it's un. This is C mod n factorial. Now this here is really a theorem, and of course we would like to do the same for the group SLN. Yeah, although, I mean, this here gives you more than just a single group, but nevertheless we would like to find out what happens here, and this is actually something that Suslin started in the early 80s. Let's see. Yes, so the one that Jim Davis mentioned is slightly less metastable, was it? Was it?
Well, I think he just put n when he meant yeah.
Okay. So now there's a paper by Suslin, and in it he constructs a homomorphism. Sort of the attempt was to, or still is, to understand what these algebraic K groups really are. And he constructed a homomorphism from this sort of complicated group, contradicting what I earlier said. So this is very complicated, to something which is simpler because it is sort of generated in degree 1, which is given symbolically by symbols, by units in the field. And this is sort of a Hurjewicz type homomorphism. And it has the property that the canonical map from Quillen K theory, from Milnor K theory, sorry, to Quillen K theory. Yeah, so this is given by observing that in degree 1, Milnor K theory and Quillen K theory are the same, and then extending this to a graded ring homomorphism. Okay, and here we go back with the Suslin-Hurjewicz homomorphism. Then this composition is minus 1 to the n minus 1 times n minus 1 factorial. So this this is relatively straightforward computation, and what he conjectured is then that actually the image of this homomorphism is precisely the image you get from this composition. So this does not see anything more. So in the attempt of understanding what this complicated group is, this homomorphism fails in the sense that it does not produce anything new here. So the image of phi n is n minus 1 factorial times k Milnor. And in this paper from 1982, he reduced the case n equals 3. This is the first interesting case due to Matsumoto's theorem, basically. And the case n equals 3 is related to Milnor's conjecture on quadratic forms. In this degree, and this was proven a bit later by Makuyev and Suslin. In this specific degree. And Suslin stated in this paper that the case n equals 4 is sort of very delicate. Now the connection between the homotopy groups of the special linear groups and this Roendigs type homomorphism, this appears in a paper by Ajok, Fazel, and Williams. This is the following situation. You have pi n SLN plus 1. You have the last column map to pi n Sn plus brackets n plus 1. So this here is Milnor-Witt K-theory degree n plus 1. And you can project down via the canonical map to the Milnor K-theory. And here you can include in SLN plus 2. And then you're in the stable range. So this here becomes the n plus first Quillen K-theory of F. And what they proved is that you place the Suslin-Roendigs homomorphism here, then this diagram commutes. And this tells us then in particular, if we know what the image here is, we know what then happens here, we know what the image here is. And this map here is surjective. And what they did was to prove the case n equals 5. So Suslin took care of n equals 3, they took care of n equals 5, and there's a gap which is n equals 4, and this is taken care of by the theorem up there. Yeah. And okay, I still have some time. Yeah.
What did you say the vertical map on the left was?
Pardon?
What did you say the vertical map on the left was?
This here?
Yeah.
This is by, oh, thank you. By including SLM plus 1 and SLM plus 2.
And you said it was subjective.
This map is surjective because the next one is then pi n of n plus 1 plus brackets n plus 2 sphere. Any further questions? Okay, would you like to see proof ingredients or would you like to see a conjecture? Okay, as my calculus class.
Yes.
Yes. This is always the right answer when you get a or question, right? So this is sort of the situation where you have a dependency on the parity, and this has to be because when you look at the real points of these objects, then there's something sort of different happens than just for the complex points. And yeah, maybe this is a bad way of stating it. So the image should be an epsilon factorial times k lim of it n plus 1. And it's even. And then it's the same. Plus eta, that's k lim of it n plus 2f. If n is odd. Yeah, so this conjecture is now known for n up to 5. And yeah, I'm very optimistic about the case n equals 6. But this is not written down completely yet. So let me just state that this conjecture then implies Suslin's conjecture. And it really describes in the first non-stable homotopy group of the special linear group. And in principle, I mean, there's sort of this meta-stable, should I call this meta-stable range? I don't know. Once you have this here, you get a few more. Maybe one more, maybe two. I mean, it depends. So. And what I did not do as preparation for this talk was to find out how the situation is for the corresponding Z2 equivariant homotopy groups of SUN with the complex conjugation action. So if anyone here knows what happens, yeah, I think this should be known, but maybe it isn't. Okay, maybe.
Non-equivariant complex case where authors after Toda that went up to 7 dimensions above the, well, seven steps into the metastable range. That was for the trivial group.
For the trivial group,
Yes.
yeah. Okay, yeah, okay. I don't know about just ZMOD2 acting. What happens there? Okay, so. If this here is true, then what you would get is y n minus 1 plus n plus 1 of SLN. This is then z to the n factorial. So this would be the sort of the motivic lift of this Borel-Hirzebruch computation. Would be a consequence of this. Anyhow. Let me just quickly sketch one proof ingredient for getting there. And there's another variety coming up, which is a simple one. It is this here, so you take pairs of vectors such that the standard scalar product is 1, and you can project down to the first coordinate. Since you have to get 1, you don't land in an, but in an minus 0. And one can check that this here is an equivalence. And what we have here on an minus 0 is an action by the multiplicative group.
What is the first coordinate, non-zero?
The first vector. The first vector has to be non-zero. Sorry, I said coordinate, right? Sorry. Okay, so if you quotient out the GM action, you get projective space. And you have a compatible GM action here, which you can then quotient out. And what you get there is then equivalent to the projective space. This now maybe looks a bit stupid, all these different notations for the same object. So I'd like to describe a map where I take one pair of vectors in this variety and a unit. And out of this, I would like to construct a special a matrix with determinant 1. So I take the inverse of u and then lots of 1s on the diagonal. And then I multiply with the matrix, which is here the degree j and k, the Kronecker symbol, delta jk, plus minus 1 times aj times bk. And then there's some algebra to check that the sort of the determinant of this here is u. So when you multiply with this here, you get a invertible matrix of determinant 1. And you can also check that when you let GM act here on Q2n minus 1, I mean, you multiply by u on the first vector and u inverse on the second vector, so this makes no difference when you multiply these here. And then one can also check that sort of, if you take the vector first coordinate 1, then 0, this lands in the unit matrix. Also, if you take u to be 1, this gives the unit matrix. So this map psi n induces a map on n minus 1 gm smash a1 minus 0. And this here is, via this projection, then the same as projector space Pn minus 1. And this here then corresponds to a one-fold suspension by this Tate circle. So we have a map from the one-fold Tate suspension of Pn minus 1 to SLN. And this is a good map. That complex realizes to a map that Yokota described to obtain a cell structure for SLN. And I don't know whether Yokota was actually the first. This is what Toda writes. Maybe Borel did it first. I don't know. So this is a good map in the sense that the cells in here are using the multiplication in this group generated by the cells coming from here. And this means that you can then get information on sort of something depending on cells, like homology, cohomology, for the special linear group for here. And this now also works sort of motivically. So the aim was to describe the image of this map, the last column projection here. And this can now, using this map, reduce to describing what the image is. Where are we? Let's see, what are the brackets? Okay, so what is this map now? Now, if you take Pn and you collapse standard sub-projective space one dimension less, this here is the same as an n plus brackets n sphere. So this here would be the sort of the projection in this situation. And the goal is sort of to describe this map. And Now, the funny thing that happens is when you look at the target here, this can be passed to the stable situation. And also here you can pass to the stable situation, and the stable situation for the projective spaces is somehow easier to manage than for the special linear groups. Yeah, so let me, shouldn't have written this here, sorry. Okay, so let me, so this is really P1 stable. Okay, so this is now a bad diagram, of course. You have a map here. Who knows what happens by stabilization? But Morel's theorem tells us that on this side, we get an identification. And this then gives us the hope of understanding what this here is. Let me just use 1 minute. So, of course, the image here, if you're in the stable situation, is the same as the kernel for the next homomorphism. The next homomorphism is induced by the attaching map for the lower projective space. So, for example, in the relevant case, the question is, what is pi 2 plus 3 P1 stable of P2, this here being A3 minus 0, and you have the canonical map going there. So we would like to understand what this here is, and this can be understood as pi 2 plus 3 P1 stable of P1 modulo the operation by eta. So this is a 1 plus 1 sphere. So we're in the range P1 stable 1 plus 2 of the sphere spectrum over F. And this group is C mod 24. So this is a computation I made with Markus Spitzweck and Paul-Arne Östwer. The generator is the second algebraic Hopf map. And there is a relation, let me squeeze it here. Eta times eta squared times eta top is 12 nu. And this means when you collapse eta, this group here is Z mod 12. And it remains to identify what element the attaching map here is. And it turns out to be plus or minus 2 times nu. And you can just read this off from topology because this is a group which does not depend on the field. It's just Z mod 12. Yeah? So topology does the job here. And this here has order 6. And this is the 6 that appears in the theorem I erased. Thank you.
Questions? Yes.
So this map that's induced from the suspension of PMM times epsilon, what so it induces an isomorphism on certain, like what is the exact property that it has?
Oh yeah, yeah. So we're from suspension of Pn to SLn plus 1. So this is A1n connected.
It is sort of the pre-block map from the previous talk.
Is it?
It goes to infinity.
Okay.
What I characterizes it by a list of 4 properties.
Yeah.
In Toda's proof of the complex version here, the n factorial arises as a composite of n maps multiplying by 1, 2, 3. I think.
Yes.
Are those individual maps? Are there kind of So they arise in a complex case. They arise from like the triple suspension of CP infinity going to the single suspension of CP infinity being compatible with the bulk map from SU to SU.
Yes, you have the same maps in this situation more typically.
So the n factorial probably comes from a composite like that.
Yes, yes. The sort of the issue is that you can actually figure out everything as Toda did in this weight. So when you're in pi, what do I have to say? Here, when you're in weight n+1. Yeah, the question is what happens in the other weights. And there it is not clear that the image in the other weights is sort of generated by what happens in this specific weight. Yeah, I mean the maps are there, and but there's information missing on how things are generated in certain degrees. You know, I mean this here is related to Quillen K-theory, and no way is this generated by elements in degree 1. For example, you have this K3 indecomposable. It's really hard to write down generators for this. So this is where the problem appears, or well, one problem appears.
So for number fields, I guess there is an open question about what is the image from K4 Milner to K4 Quillen. Does this shed any light on this? So it depends.
It depends on whether you have a sort of real or complex field, right? I mean, totally imaginary or totally.
Yeah, no, it's only if you have some real embeddings.
Yeah, yeah.
I think it's a non. I looked at this with Chuck Weibel 20 years ago, and we couldn't quite pin it down. I mean, I think it's the only dimension where there's an open question about the image.
Okay. Yeah.
Because in K5 and higher, the image is 0, and in K3 and lower, it's understood. But in K4, there's still a question.
Yeah, I think what Suslin did when he attempted to prove his conjecture in the next sort of case was to look at number fields. And he has notes on this that I have not seen, but someone else has seen. Maybe there is something, but I don't know whether this helps here.
I think the potential image is something which would go to 0 again under this composite map. So it feels like we're not actually doing anything about that particular point. Other questions? Not, and now I believe there are drinks in